Welcome to the American Shoulder and Elbow Surgeons podcast. I'm your host, Peter Chalmers, a shoulder and elbow surgeon at the University of Utah in Salt Lake City. Before we get started, I should mention the views expressed in this podcast do not necessarily reflect the views of the American Shoulder and Elbow Surgeons Society, the University of Utah, or the institutions of any of our guests. Okay, today we have a special episode for you on shoulder biomechanics. Now, biomechanics plays an important role in everything we do in caring for shoulder and elbow patients, from understanding how the pathology influences the functions of the shoulder to understanding how to repair or reconstruct the pathology in a manner that will most likely result in success. So we're really indebted to biomechanical engineers in our field, but I think there can often be confusion. How do we interpret the findings from biomechanical studies? What questions can or can't be answered with these types of studies? And to discuss, we've invited two world-renowned experts. Both are PhD biomechanical engineers. Both have made huge contributions to our field. So first, from the American Sports Medicine Institute in Birmingham, Alabama, we have Dr. Glenn Fleissig. Glenn, welcome to the podcast.
Thanks, Peter. Welcome to be here. Happy to be here.
And then next from the University of California, Irvine, and the Congress Medical Foundation, we have Dr. Ty Lee. Ty, welcome to the podcast.
Great to be here.
Well, I'm really excited to have both of you guys on, and I wanted to kind of start with the basics. So, Glenn, how did you first become interested in biomechanics?
Oh, that's a long time ago, 150 years ago when I was a college kid at MIT. I majored in mechanical engineering back in the 1980s, mechanical engineering. And then as a senior at MIT, you have to do a senior project. And just wandering around MIT in mechanical engineering, there was some people building car things and some people welding things and other mechanical engineering labs. And one lab, they were analyzing golf swings. And as a guy who likes sports, and I'm like, I could do this. So I never heard the word biomechanics. This was 1983. I never heard the word biomechanics till I wandered in that lab. And I learned at that point that mechanical engineering could be applied to this up-and-coming field called biomechanics, which is essentially applying mechanics to people.
What about you, Ty?
Well, I had a similar path as Glenn. I was a mechanical engineer, and I happened to be touring Dr. Savio Wu's lab, and I saw a first orthopedic implant. It was just a hip implant. It was pretty simple, but I thought it was the coolest thing I've ever seen. So since then, I was just hooked. And then right before that, I was doing cardiovascular mechanics a little bit. And I just didn't like that because there's too many things that I could not control. In orthopedics, you can control many more things. So I was just turned on by implants and never looked back.
I think it's interesting that both of you have kind of mechanical engineering backgrounds, which is it's so useful. So I wanted to talk a little bit about that. You know, we, as orthopedic surgeons, one of the primary ways we interface with biomechanics is in the literature. And when we see a cadaveric biomechanical study, there's a lot of things that are reported. There's stiffness and gap formation and load to failure and failure mode. Now, Ty, you've done a lot of these kinds of studies. When you look at a study like this, how do you evaluate those findings? Like which of those are most important from the surgeon's perspective? What do those numbers matter? Which of them don't matter? What are your thoughts?
I think the one of the critical flaws that I see in some people writing these papers is that they love to report stiffness and ultimate load. And those two are the main two things. And those two parameters are useful, but they basically represent catastrophic failures. And I think as orthopedic surgeons should be more interested in low end of the loading curve, such as initial stiffness, linear stiffness, hysteresis, cyclic loading behavior. It's all in the functional range that should be more interesting. And generally, I mean, I think orthopedic surgeons, they worry about strength the most, which you should worry about. But the goal is the initial time zero right after the surgery. You just want to get them through the rehab so healing can occur. It's not going to stay in that strength forever. So you should be more interested in restoring its physiological load, structural integrity, more than the ultimate failure. So I think they're all important, but I think there's less focus on the low end of the loading curve, which should be more emphasized.
Peter, I just want to jump in. I know this is more Dr. Lee Ty's specialty there, but I was going to say the same thing because one of the things people measure in these biomechanical studies is stiffness, and it's misleading to think that the stiffer is always better, because if you're trying to reconstruct or replace a certain ligament or tendon, I don't think you want to be twice as stiff or stiffer, you pretty much want to match the stiffness. So because you don't want to put a steel rod in for a ligament or tendon. You want to match the stiffness, not the more stiffness, the better. Would you agree, Ty?
Absolutely.
One of the things that I think is really interesting, you guys both brought up, and Glenn, I know you guys have done a lot of this work at ASMI too, so I'm really interested in your perspective on this for sure. Not just Ty, but both of you. One of the things you both mentioned is you would look at the low end of the loading curve because that's maybe where the more physiologic loading is. And one of the confusing parts I find with these studies is, for instance, you might look at a study and it'll say, well, the biceps tenodesis fails at 400 newtons. And I look at that and I think, well, how many newtons does the average person put through their biceps? And how much weight would someone have to lift to put 400 newtons through their biceps? What are your thoughts, Glenn? You've done a lot of motion analysis work. How do we answer those questions? Like, how do we determine what the actual in vivo forces are when people use their arms?
Yeah, excellent question. So, Ty was talking about you pretty much want to study fatigue and overuse and long-term problems, but there are situations where we do want to know the maximum load and acute. And a big example of this is throwing or baseball pitching. And so, in the motion analysis biomechanics lab, we do us at ASMI and other places have done biomechanical studies of baseball pitchers of all types, from major leaguers to little leaguers, and using in what's called inverse dynamics, we could use the cameras and the computers and capture people's motion and calculate the estimated forces on their shoulder and on their elbow, etc. And then these are the types of loads, which are high loads. These are the type of loads we could really put the cadavers through in the cadaver lab, or put the surgically reconstructed or repaired shoulder or elbow through in the cadaver lab. So in these cases, we know what load and also what speed these arms are going at during pitching. And in our cadaver studies, we pretty much can't simulate that. We can't make the cadaver arm move as fast or accelerate as fast as the baseball pitcher, but we have a sense for what the maximum load it could handle is, and then we could really put kind of high loads on the elbows or shoulders in the cadaver lab, both the natural and then the injured shoulder or elbow, and also the surgically reconstructed or repaired, and compare them at this high level of force or torque.
That's great. I wanted to ask you a little bit about this. There's a hiding in the middle of your answer is you use the term inverse dynamics. Tell us. So how do you get from someone in your lab is throwing a baseball to the force? Like, what are the steps there?
Sure. First of all, the answer I would have told you 20 years ago is, like you said, in our lab we would study it. Now the answer is in our lab or on the field, and we could get into that later. But there's also technology for collecting it in games. But in our lab, typically, we have a baseball pitcher. We have motion analysis or motion capture. We have anywhere from 6 to 15 cameras are spread around. The cameras go at high frame rate, and they are all connected to a computer. So it's the same type of technology we use in biomechanics labs, but it's also used in entertainment, like for movies, special effects, and for entertainment games. So essentially, a person does whatever they do. In the lab, we'll put the reflective markers on them. The new technology is you don't need reflective markers if you have a certain type of system. And the cameras will figure out where in space in the lab or in the field the person moved, meaning where was their arm and how fast did it move and how fast did the trunk move. And then you see where's the arm compared to the trunk. What I'm getting at, Peter, I'm not going to get too far down the rabbit hole here, but this guy, Isaac Newton, said force equals mass times acceleration. So
I've heard of him. Yeah, he's
okay.
He's one that he's buried deep inside, but I heard of him a long time ago. That guy.
Yeah. So dynamics would be you know the force, and then you determine the mass or acceleration. Inverse dynamics, as I said, is we know the mass of the person, their weight, and then the acceleration of their arm from the camera, and then we inverse dynamics from the acceleration of the arm multiplied by the estimated mass of the arm. we then calculate the estimated force on the arm or torque. So force equals mass times acceleration. We get the acceleration from the camera watching where the arm moves. We get the mass of the arm from, in the literature, it says an arm weighs a certain percent of a body typically. So that's the most common way to do it. And the mass of the arm for this guy weighs 200 pounds. So his arm must weigh so many pounds. And then his arm accelerated at a certain speed, and acceleration times mass, we calculate, boom, the force on his shoulder or elbow.
I think you're making it sound easier than it is, but I understand the underlying concept. Now tell me, one of the things that I think is important to discuss is, you've made huge contributions here. We've written a lot of these pitching motion analysis studies that have really changed, I think, the way we look at the pitch, and the way we treat baseball players. What are the limitations to these studies? Like, what are the questions they can answer, and what are the questions that they really probably can?
Sure. So the first limitation, I started ASMI in 1987 with Dr. Andrews and colleagues. And so, our cameras and computers have changed. But one limitation along the way, the cameras are super accurate now in computers. But one limitation along the way is, I just said, force equals mass times acceleration. So one limitation is calculating the mass of the upper arm, the mass of the forearm, and just using a standard formula and saying everyone's forearm weighs a certain percent of their body. That's an estimation. The other, and that's what we have to live with. And the other estimation is the performance of the athlete in the lab. I mean, the radar gun doesn't lie. In the lab, the guys who are throwing 95 in games are throwing like 91 in my lab, 91 miles per hour in the lab. It's fast, but clearly they're 100% motion. I mean, they're giving it their full try, but I don't know, the adrenaline's not flowing or whatever. So that's the limitation biomechanics has had in sports biomechanics forever. But the saving grace, Peter, is that if I'm comparing my mechanics to your mechanics, or whatever, we're both, let's say, a little off our game, but probably the same little percentage. So there's a much bigger difference between my mechanics and your mechanics than between your mechanics in lab and your mechanics in game. So that's one of the problems that we're doing in the lab. But I don't really think it's a big problem because everyone is studied there, and you can compare things pretty good.
And what do you think, Ty? I mean, you've done a lot of more cadaveric biomechanical work. What are some important limitations to that work that we should take into our reading of the results and conclusions of those studies?
So I think studies like Glenn does is really good because it takes the performance of the entire athlete. The limitation of biomechanics is cadaver biomechanics is that we have to separate out stabilizing mechanisms. For example, the bony stabilizers and passive soft tissue stabilizers and the muscles, and how they all work together. And in order for cadaver studies to be done well, you have to isolate the variables. If you leave too many components onto the system, then you end up with an indeterminate problem. So we spend a lot of time trying to isolate what it is. So in the earlier days, we used to just cut things out and study isolated tissue properties. And now we're getting a little more sophisticated, so we can do more strain field analysis, better kinematic analysis. In cadavers, we use the basic same technology as Glenn does, except we use it for strain fields and we use it for kinematics of each individual bones and things. So the major limitation in cadaver studies is that you cannot incorporate all the parameters that goes into joint function. So you have to take it for what it is. But for orthopedic field, I think cadaver biomechanics is very important, and I find it useful for the industry and the surgeons, because when surgeons operate on a patient, it's usually targets in one region or one structure. So how you can best restore that structure is a question. So it's useful in that way, but the limitation is that we have isolated parameter.
Peter, can I ask a follow-up question to Ty? I know I'm the guest here, but
Please.
Ty, when I study the elbow in the cadaver lab and do varus and valgus, it's pretty simple. It's a hinge joint and going in one direction without much muscular activity in resisting that in a human. But in the shoulder, you have a lot of muscles and tendons and all over the place. And so one of the biggest challenges is in the dead guy, his muscles are not firing or tense. So do you want to explain a little how you deal with the issue about muscles and tendons in a shoulder cadaver study?
Sure. I've been studying this for over 30 years, and there's no real way of trying to simulate all the muscle forces properly. As far as providing joint function, it's all about degree of freedom for the joint, and you understand that correctly, and your setup has to accommodate that. So as far as shoulder function goes, we have to make certain assumptions, and at least what I have been using, which made the most sense, which I've tried all different combinations, is that I use proportions of the muscle forces. And then I try to keep all my studies to quasi-static type of studies. That dynamic studies, we have all the things to do. Dynamic studies, we can make the shoulders move, but the thing is, you can't get consistent results because you have the tissue properties, you have the length, you have shoulders in such a way that even sequence of muscle loading makes a difference. And it's the most mobile joint in the body, so it goes all over the place. So it depends on what path you choose, you're going to get a certain thing. So how do we know that what path we need to choose? We really don't. So that's why I went to proportional muscle loading to just try to isolate that parameter, and you have an internal control so you can see the effects of your procedures or injuries that you're trying to create. Did that answer your question, Glenn?
Yeah, definitely. And I learned something there. And I do agree that when we do our studies, even though we do baseball, we're trying to talk about baseball pitchers and other throwers, we do what you said, quasi-static. And again, that word to me means the cadaver is being moved, but it's being moved at a slow rate, not trying to reproduce the dynamic explosive rates in a human. It's moving, but slow. So we call it quasi-static.
Yeah.
One question I had for both of you is about the tissue itself. For instance, Glenn, you mentioned that you're doing elbow biomechanics studies about UCL repair and reconstruction. That's a surgery we typically do on 18-year-olds. I think most of our cadavers are probably, again, they come from those that have passed away. So most of them are probably elderly individuals. Some of them have been frozen and thawed and then frozen and thawed. How do you both try and account for the tissue quality in your studies, and how do we control for that? Maybe
I'll go first.
Yeah.
Yeah. Well, first you have to make sure tissue is fresh. And the second thing is, I jokingly say that we always do experiments on elite elderly throwing athletes, but that's actually not true at all. But I think structurally they remain relatively the same. There's age-related property changes, but I think tissue itself, it probably is a little stiffer and so forth. But orthopedics is more procedure-based. There are tons of mechanical studies done on aging and specific tissues, insertion sites and bones, have you. So all those is there. So it depends on what question you're asking. Is you need to design a study to answer the question that is to you. So if you're truly trying to study the difference between younger and older specimens, or the difference between younger and older with respect to tissue quality, then you're going to have to find a way to get younger specimens that are pitchers, which is impossible to do. So one of the things I always do with surgeons, I work with a lot of surgeons, is really clearly identifying what your question is and have that down into really clear question. And then us as engineers or scientists, we can actually develop methods to answer that specific question. So at the end of the day, you have to make a lot of assumptions, but you have to design a study to answer the question, and that becomes relevant. So that's going to determine quality of the study.
I don't have too much to add to that. As Ty said, the first thing is you want quality specimens in that they're fresh frozen. It seems to work out well. Sometimes we ask for just male instead of female. Sometimes we even just ask for right arms instead of left arms if we're trying to do pitchers, something relative to throwers, we never say under 30 years old or only. They're not going to be baseball pitchers. We sometimes say under 40 or under 50, which takes longer to get the specimens. Fortunately, less people that age die. But essentially, as Ty was saying, you just have to design the studies. The in vitro studies are not simulations of actual human motion. So we could learn a lot from the cadaver studies, such as, like you said, how strong is the natural tissue compared to the reconstruction surgery technique 1 versus surgery technique 2. You could learn a lot without being the exact loads or the exact quality of specimens.
So basically, we approach the joint as a structure, and we're doing a structural analysis.
Now, biomechanics is often described as the application of common sense. So, for instance, like a biomechanical study showing that 2 plates provides higher stiffness in a fracture fixation construct than 1 plate might be obvious. You may say, well, we didn't really need that study to show that more screws or more plates is better. I think both of you have been really clever in the studies you've designed to create findings that change practice and maybe sometimes tell us things that were not so obvious. So tell us a little bit, as you approach questions, how do you design studies that can reveal that which would otherwise be obscure? What are your thoughts, Glenn?
Yeah. Okay. So again, staying with the in vitro, the cadaver studies, Peter, or all studies, or what are you asking me?
I think either way. I mean, both of you are scientists, and I think this is an interesting question scientifically.
Okay, I'll leave to Ty to talk about the in vitro cadaver ones. I want to talk about the in vivo motion analysis ones. When we started ASMI in 1980, I love what we did. Essentially, it was a getting together the brains of the orthopedic surgeons, the physical therapists, the biomechanists, and the coaches. And it was really interesting. When we got together, we would watch a baseball pitcher, for instance, and I'd say, "Oh, I see that the torque on the arm looks high." I say, and the coach would say, "I see he's stepping across and dropping his arm." And the surgeon would say, "I see he's loading his rotator cuff." We'd all see different things in different terminology. But what we've always tried to do at ASMI is try to solve the important questions. We're not trying to solve the questions we can answer. We're trying to answer the questions that are important. It's very easy or lazy just to study what you're able to study. It's more important to ask the clinicians, the surgeons, the coaches, the physical therapists, what's the important question, and then studying it. I want to just give an example. We've been in baseball, a big issue is the interval throwing program. Peter, you're very familiar with that, and as many of the listeners are, and that after a person has a surgical or non-surgical treatment for their elbow or shoulder, as a baseball player or other thrower, they go through an interval throwing program, which is they throw flat ground and back up, and then they go on the pitching mound if they're a pitcher. Well, that was designed by clinicians, physical therapists, but we've done biomechanical tests to see what is the force on a flat ground throw compared to a pitch. What is the angle? What are the motions of pitching at half effort versus 3/4 effort? So I think in biomechanics, again in the motion analysis lab, we're trying to study the questions that are not of interest to me, but are of interest to the clinicians, whether the coach, the surgeon, or the physical therapist.
So I'll follow up with that. I'm 100% agree. I think our field exists because of orthopedic surgeons. They bring us a question and we try to answer the question. Peter, what you were saying is exactly right, that I frequently have it in my lectures saying that orthopedic biomechanics is not rocket science. If it doesn't look right, that means you're probably doing it wrong. But what orthopedic biomechanics does is that it tells you how much. So we know something's going to be stronger than the other inherently or by design, but we don't know how much difference it makes. And also, the other important factor is this is the information that I get from my other scientists and research that Glenn does, is we need to create the boundary conditions same or similar as possible as in vivo conditions. So we try to get close to that. So certain things may be structurally really strong in one direction, but may not be in the other. So we have to create that condition, and we can tell you how much if you design this study correctly. So, for example, let's say biceps tenodesis. Obviously, you have to make it strong enough. You have to create a healing environment, but how strong? So if you have a more robust repair technique that's going to match the physiologic loading at the functional level, and it ends up being much stronger, meaning that it can maintain that condition at much higher loads, then you can rehab them much quicker. So every biomechanics question, once you put those numbers to it, that it has clinical relevance at how surgeons can take that information and use it for the patient to make them better.
What I love about what both of you said is that you guys both see this as a collaboration with surgeons, and that's I think one of the things that most orthopedic surgeons enjoy is working on teams. Many were team athletes in high school or college. Certainly, surgery is a team sport where you must participate with the scrub and the circulator and all of the anesthesiologist. And clinic is the same way. You have to interact with, your PA or your MA or whoever's helping you in clinic, and they're only by working as a team can we succeed. It sounds like for both of you, that's the way you see science, and I think that's so heartwarming to hear both of you say. It's great.
Yeah, definitely agree. Yes.
Yeah, that's what makes it fun, because I can study everything I want, but it may be clinically relevant, it may not be. But obviously, when you have a clinical impact, it makes science better, not making it just curiosity thing.
So I wanted to ask you guys both, there's a lot of the listeners to our podcast are younger surgeons. They're medical students or residents or, orthopedic surgeons that are early in their career. And I think a lot of these people, they have great questions. They approach our pathology and our procedures with fresh eyes, and then they can come up with fresh ideas. So if you had to give advice to someone who's a student or a resident or a fellow or a young surgeon who has an idea of something that potentially could be studied in the biomechanics lab, about how do you become as a surgeon the best collaborator with the biomechanical engineer, what advice would you give? Ty, what do you think?
Well, first advice I would give is do a good lit search. Nothing kills a great research idea like a good literature search. So that's the first thing I ask them. And second thing, I actually have a lecture on this. Second thing I tell them is, well, is it going to make a difference? What are you really trying to improve? And then a lot of times I'll get a response saying, but it hasn't been done before. We don't know the answer. And I said, just because it hasn't been done, it doesn't mean it's worth doing it. So I have them think through their questions, good lit search. And then it doesn't matter who it is. I work with a lot of people around the country. Anybody can approach me. If it's a good idea, I'll work with them. But the main thing is that they need to think things through, and I have them give a presentation, and I go through. But other scientists may not make you jump through all those hoops, but I think it's really important. But as young surgeon residents, whoever's starting a new research project, the good literature search is critical. That's number one thing. And then a lot of things will become much more clear as they read more.
Oh my goodness.
I know, Glenn.
I just want to jump on one thing that Ty said. It's so true. Just because it hasn't been done is not a good enough reason to do a study on it. I mean, there are a lot of things that haven't been done. Can people with purple shirts jump higher than people with green shirts? I don't think anyone's ever done that study, but what a waste of time that would be. So just because it hasn't been done is not a good enough reason. If I may, I'm going to add to some excellent points Ty just brought up. Another advice I would give to the young surgeon is what you were saying, Peter. This is a team sport, as we all like team sports. And if we look at our heads, we have one mouth but two ears. So when you get together with the biomechanist or the scientist, do some talking, but probably do twice as much listening. And really, I've been blessed to work with Dr. Andrews and some other orthopedic surgeons who don't just talk and have this huge ego. They listen also. And I listen also. We have to design the problem and do the study and analyze the results, looking but also listening as a group.
So that's a great point. Is listening. The the other point that I want to add to that is that every time I do a study, whether it be residents or students or surgeons, I make them understand every single step of what we're doing. That way they can jump in, because sometimes, I mean, it hasn't happened to me. Hasn't happened to me yet, but a lot of times when I talk to people about research, the surgeon will come with an idea, and scientists will do the study, and then the answer comes out totally different than what they thought. And a lot of times, surgeon's feedback would be, "Well, we didn't do the study right." The one advice that I would give young surgeons is that don't have a preconceived idea of what you want to see, because if you want to find certain findings, you will find that you can design a study to find it. You want to go into it in an objective manner.
Now, both of you have done a lot of research, and I'm sure reviewed and read a lot of research, over the years. I wanted to ask both of you, what is your all-time favorite biomechanical study, and why is it your favorite? And you can pick one of your own, or you can pick someone else's. I think either is fine. What do you think, Ty?
I'll let Glenn go first. I heard that last time that
Perfect. Yeah.
Okay, I'm going to try not to sound obnoxious or cocky, but I think my favorite one is the study I did with my group in 1995. Me and Dr. Andrews and the late Dr. Chuck Dillman, we did the kinetics of baseball pitching with implications for injury, and it's really the seminal work in this baseball biomechanics. And again, I did a lot of listening to Dr. Andrews about what injuries he's seeing, and I mean, this is 30 years later or so, and I still think that paper, that 1995 paper, is kind of the grounds for our understanding. A lot of it still holds true about how baseball pitching leads to injuries and the mechanisms. I'm really happy with that one.
So my favorite study out of my papers, I mean, obviously I'm a little biased. I think there's two aspects. One is contribution of muscles to glenohumeral stability. In the old days, we used to just think about rotator cuff muscles, but even involving the muscles were challenging in the old days. But as we went along, we we truly understand importance of pec and lat and the deltoid, which comes into play a lot in reverse shoulders and so forth. So that's one. And second thing is, which is something I had trouble with, maybe Glenn can comment on it. American Society of Biomechanics kinematic, method of determining kinematics of the shoulder was not specific enough to the glenohumeral joint. So me and my postdoc ended up developing a whole new kinematic algorithm to determine exact glenohumeral kinematics, which is just exact movement between humerus and the glenoid. So those are two of my favorite studies. They're not cited as much as other like rotator cuff studies, but from my perspective, they're the favorites.
Peter, I just want to add something. You're saying what's your favorite article? Dr. Lee, Ty, and I have been doing this a long time. When in 1980s, when ASMI started doing baseball pitching biomechanics or throwing biomechanics, we were essentially the only show in town. And then in the 1990s, essentially the only show in town. And there would be about 20 articles published in the literature every year in baseball biomechanics, of which, maybe we were doing half. Nowadays, we're still doing about 10 a year, but nowadays there are about 200 papers per year on baseball biomechanics published. It's just been exploding. And I'm really happy to see that we're not the only show in town. And what's happened in the last 10 years or so is baseball biomechanics in particular has really, you know this, Peter, this has really become a thing, a profession, a field. And we started what's known as the American Baseball Biomechanics Society because so much was happening. And the website I want to plug is baseballbiomechanics.org. It's free for orthopedic surgeons or biomechanists to join. And we're really starting the communication to standardize what we're trying to study in baseball biomechanics. I mean, major league teams are hiring biomechanists now, so we're really, and universities have it going also. So we're really trying to standardize it. And there's so much literature published. We've started this society, and I encourage people to look into this.
I'll be joining.
Okay. Right.
I need to join too. I didn't know that, but it sounds awesome. I think this is the other thing that both of you have mentioned that I love, that I think both of you have a real love for the field, and that it's so collaborative, there's not a competition between one lab or another lab. I think we're all, playing for the same team.
Well, fortunately for Ty and me and other biomechanics, there's not a lot of salary to be made or millions of dollars to be made. So we don't have to compete. And we do, we're just kidding. But seriously, I think there is a collaborative method of it. And also Ty and myself and others who are into biomechanics, I think a lot of us really love it and enjoy it. It's what we want to do, the science of life, of people as they become elderly, or of people being athletic. And I think I could speak for both of us. We really enjoy it. I love going to work and doing this.
Yep. Otherwise, we wouldn't have written all those papers.
You too, you too, buddy. You too, buddy.
Well, I want to thank both of you for coming on. I mean, you guys, as I mentioned earlier, have made huge contributions, and your insights here for listeners about how to evaluate these kinds of studies and how we can really use the biomechanics to improve our care for patients are really valuable. That's about all the time we have for this podcast. Thanks so much to our guests. For all of our Shoulder Nebel listeners out there, don't forget to subscribe, and we will see you next time.